Here I've got a mid to late 1980s Radio Shack remote control unit, which would have been used to control a toy car probably, or a toy boat. In this video, I'm going to use some sophisticated test equipment to analyze the signal, the power that comes out of it, the modulation scheme, and various things like that. And I'll attempt to design a circuit to receive all that and to control something. I'll do that in the next video, but in this video I'm just going to go through and analyze the signal that comes out of this. With the top cover off, you can see that the circuit is pretty basic. It uses two joystick type switches, I guess you'd call them, for the forward and reverse, and right and left. There's some capacitors, diodes, and the main chip in there, and a crystal, of course, and an on-off switch. So you can see that the black thing on the middle, kind of in the middle, is the chip that does everything. The little silvery thing just below the switch is the crystal, and there's a couple of iron core inductors there. That's probably one's for the frequency, and an LED to basically say your transmitter is on. So it's a very basic circuit, and it's probably going to be pretty easy to figure out what's going on in here. There is an antenna, which this didn't come with the original antenna, so I had to make a simple one out of a piece of wire. But that shouldn't change anything in the distance it can work at. These were designed for maybe up to 50 feet at most, so it puts out very low power. But I'm going to determine how much power comes out of it. On the bottom is a 9-volt battery, and right there it says the frequency that it's supposed to put out, 49.855 megahertz. Here I've put it on a frequency counter, and it's putting out 49.9309 megahertz. That's pretty good. Very close. If I wanted it to be exact, I could tweak it, but it's pretty good. And I'll leave it at that. Here I've put the signal on the oscilloscope, and I get a sine wave, but it's jumping around. It's being modulated at a lower frequency, and that doesn't tell me a whole lot, except that there's a signal there and it is a sine wave. I'm going to have to put on the modulation probe to look at the signal itself and see what is riding on top of that. Before I put the demodulation probe on this, I want to see if it's putting tones on the carrier or what it's doing. So I don't hear anything right now. This device here is a type of spectrum monitor, kind of a handheld spectrum analyzer, signal strength meter, and it gives me it will demodulate any tones that are on there. So I'm going to push this forward. I don't hear anything right now, so I'm going to put it in the forward. There we have a tone and a lower tone there. So forward is now. Let's see what happens if I push this forward. Okay, so what happens is when I go forward and I push this to the left or right, it changes the tone of the forward tone. It changes it slightly. And then when I put it back, this left or right changes the tone of the reverse signal. So we're going to have to investigate that further and see exactly what's happening. Now here we see that the control is in the forward position, and I'll freeze it, and it says the frequency is 926.879 hertz. We have 55.2% duty cycle. And we have, when I put it into right, get it out of the freeze mode. When I put it into right, it says 69% duty cycle. Then when I put it into left, it says 41. So from left to right, it goes from 41 to 69% duty cycle. This is in the reverse mode. We have a frequency of 393.7 hertz, and the duty cycle is 54. Now we'll unfreeze it and look at the duty cycle when we're going back left. It's 35.8%, and when we go right, it's around 75, something like that. Here I've managed to capture the carrier as it's being chopped at 926 hertz. This is the forward signal. Here I've got the remote control transmitter terminated across 50 ohms, and using an RF voltmeter, I am measuring that the voltage that it's putting out is 232.2 millivolts. One nice feature of this RF voltmeter is that it's got an analog power scale, which measures out in dBm. As you can see there, it says 0 dBm. 0 dBm is 1 milliwatt across 50 ohms. So 1 milliwatt is 1,000th of a watt. Very low indeed, but good enough for 50 feet. One interesting thing you'll notice about this type of modulation is that when I add modulation to the carrier, either reverse or forward, it goes down by about 1/2 of a dB. And the voltage drops too, quite a bit, from 232 to 217. Here I did something I thought might be interesting. I took the actual output of the remote control and I put it on a milliwatt meter. And with the unmodulated carrier, I've got 1 milliwatt coming out. And then when I put it into forward mode, it drops down to 60%. And when I put it into reverse, it's 60%. Forward left is 40%. And forward right is 80%. Reverse left is 40%, and reverse right is 80%. This device is called a bolometer type watt meter. And here is what is known as the bolometer head. The RF comes in one end and heats up basically a resistor, and you have a very sensitive thermistor not directly attached to it, but so that heat can be transferred between the two. And the actual meter is just electronics to display an equivalent power for that particular input. So these are very accurate, and any type of
RF wave can go into it between the frequency limits. This particular bolometer head is good up to about 12 gigahertz and will go as low as 30 or 40 megahertz, and it's accurate a whole frequency range. Here we are going to summarize the information that we have figured out previously from using various pieces of test equipment. The frequency of the remote control is 49.9141 megahertz. The forward modulation is 926 hertz at 56% duty cycle. Reverse modulation is 393 hertz, 56% duty cycle. Forward left is 41% duty cycle. Forward right, 69% duty cycle. Reverse left is 35.9% duty cycle. Reverse right, 72.9% duty cycle. The output power is 1 milliwatt or 0 dBm across 50 ohms. And the power drops 50% at 50% duty cycle.